Try combing your hair when it is dry, and then removing the comb over scattered bits of paper. You will find the pieces of paper get attracted to the comb. This is what happens when two objects are rubbed together. They become electrically charged. This is how the comb gets charged when you run it through your hair, and then attracts the pieces of paper. You may wonder where the charge comes from in the first place. Well, matter is made of atoms, and all atoms consist of charged particles. Are the charged particles arranged in any particular manner? Are the charged particles spread throughout the atom, or are they concentrated in one place? To answer these questions, let's go back in time. Dalton's atomic theory stated that an atom was indivisible and indestructible. However, in 1886, Goldstein came upon positively charged radiations in a gas discharge, which he termed canal rays. These radiations led to the discovery of the proton. The mass of a proton was about 2,000 times that of an electron, and it carried a positive charge. Around the year 1900, J. Thomson conducted experiments on the beams of particles inside a glass tube called a cathode ray tube. He found that the particles were attracted to the positive terminal of the tube. Thomson concluded that the particles must be negatively charged and called these electrons. An electron has a negligible mass and has a charge of -1. These discoveries made scientists believe that an atom was divisible and made up of electrons and protons. What they didn't know at that time was how the electrons and protons were arranged within an atom. They tried to understand this arrangement through various experiments. This lesson introduces you to different models related to the structure of an atom. By the end of this lesson, you will be able to. J. Thomson was the first to put forward a model to explain the structure of an atom. In his model, Thomson compared an atom to a Christmas pudding. The electrons were like the raisins in the pudding, and the pudding itself was like the positively charged particles. This can also be explained through the example of a watermelon. The positive charge in the atom is spread all over like the red, fleshy part of the watermelon, while the electrons are embedded into the atoms like the seeds of the watermelon. The oppositely charged particles are held together by electrical force of attraction. Thomson concluded that an atom consists of a positively charged sphere with electrons set within the sphere. An atom is electrically neutral as the positive and negative charges within it are equal. Thomson had said that the electrons were embedded in a sphere of positive charge. This turned out to be incorrect. Thomson had explained that the positive charge spread through the atom held the negatively charged electrons due to electrical forces. This assumption failed to explain many experimental observations made by other scientists. Thomson's student, Ernest Rutherford, conducted an experiment using gold foil, which disproved Thomson's model. For his experiment, Rutherford used a gold foil which was about 1,000 atoms thick. He made a narrow beam of alpha particles fall on the gold foil. Alpha particles are doubly charged helium ions and have a mass of 4 atomic mass units. The result of the experiment was unexpected, as it did not follow the structure of an atom as known scientists at that time. Rutherford found that most of the alpha particles passed straight through the gold foil without getting deflected. A small fraction of the alpha particles were deflected through small angles. A few alpha particles bounced back. Based on these observations, Rutherford concluded that most of the space inside an atom is empty, as most of the alpha particles pass through the foil without getting deflected. Very few particles were deflected from their path. This deflection was caused by the repulsive force of the positive charge in the atom. The positive charge was concentrated in a small area within the atom and was not spread throughout the atom as Thomson had proposed. Based on his observations, Rutherford proposed the nuclear model of an atom. The positive charge is concentrated in the center of the atom, which is called the nucleus. The electrons revolve around the nucleus in circular paths called orbits. The nucleus is much smaller in size than the atom. According to Rutherford's model, the electrons, while moving in their orbits, would give up energy. This would make them slow down, gradually move towards the nucleus, follow a spiral path, and then fall into the nucleus. Ultimately, the atom would collapse. In reality, however, an atom is stable. Therefore, this particular assumption made by Rutherford was inaccurate. Keeping the shortcomings of the Rutherford model in mind, Niels Bohr formed his postulates about the structure of an atom. Electrons have discrete orbits called shells inside an atom. Electrons revolve in their orbits without radiating energy. Within a particular orbit, the energy of an electron is constant. This is why orbits are called stationary orbits or stationary shells. Orbits or shells are also known as energy levels. Shells are represented by the letters K, L, M, N, or the numbers 1, 2, 3, 4, and so on, depending on the number of shells in the atom. However, Bohr's model did not apply to elements like helium and lithium. The model was also unable to explain the structure of chemical bonds. Despite the limitations of their atomic models, the work of Thomson, Rutherford, and Bohr is considered path-breaking. All three scientists received Nobel Prizes for their theories. Therefore, these three atomic models are the foundation for our present-day understanding of the structure of an atom.